All right, so this next video is about what the overall purpose is of this lab. Hopefully you have an understanding of how titration works. You calculated the concentration of sulfuric acid correctly. And this is the purpose of the overall lab. The goal of this lab is to determine the rate law for the decomposition of hydrogen peroxide. Hydrogen peroxide decomposes into water and oxygen gas. Is it a zero-order reactant, a first-order reactant, or a second-order reactant? And from the coefficient, we can't necessarily tell, and you'll learn why later. So our, again, goal is to write the rate law, to figure out what the order is for hydrogen peroxide, and then we'll be able to, through graphical means, determine what that value is for K, using the correct slope of the correct line. All right, well, how do we do that? Well, there's a reaction that can happen between hydrogen peroxide and the permanganate ion. And we'll learn how this works later when we get to our electrochemistry unit. It's a redox reaction, an oxidation-reduction reaction. But what happens is hydrogen peroxide and permanganate, in the presence of acid, there's got to be an excess of acid here for this to work, turn into water, oxygen, and the manganese ion. The manganese ion. The key to this reaction is that the permanganate ion is bright, vibrant purple. It's purple. The manganese ion, on the other hand, is colorless. So if you add a small amount of the permanganate ion to an excess of hydrogen peroxide, all of the permanganate will react and it will become colorless. We're going to be adding permanganate to hydrogen peroxide, and initially it will be colorless because all of the permanganate turns into manganese, which is colorless. But at the equivalence point, the point at which moles of permanganate equal moles of peroxide, or any point past that, then permanganate is in excess and the solution remains purple. Adding any permanganate past the equivalence point will result in the solution being purple. At that equivalence point, we know that moles of permanganate equal moles of peroxide, at least stoichiometrically. You've got to balance it and account for the coefficients, which allows us to then know how many moles of hydrogen peroxide were in the analyte flask, and that's going to allow us to calculate the concentration. It's a pretty tricky technique, which I'll do here in a moment, but what we're going to be doing is adding permanganate over time to hydrogen peroxide as it's decomposing. We're going to set up a reaction flask where hydrogen peroxide is decomposing, and every 6 or 7 minutes I'll be pulling hydrogen peroxide out, adding permanganate to it, titrating against it to be able to then calculate how many moles of peroxide were in the flask at that moment in time, therefore what the concentration was, such that we can graph the concentration of peroxide against time at 6 various time points. And if that's not linear, we know it's not zero order. If concentration against time isn't linear, we know it's not zero order. We'll manipulate the concentrations into natural logs, see if that's linear, and if it were, we would know it's first order. But if it isn't, then we graph inverse of concentration of peroxide against time, and if it's linear, then we know it's second order. So again, the goal is to determine the rate law for the decomposition of hydrogen peroxide, what the order is, and the way we do this is titrating peroxide with permanganate ion, looking for the color change, which allows us through some calculations to figure out what the concentration is at various time points, which can be graphed. All right, good luck with your questions. I'll be back with you shortly for video 3.